Okay, so we will start yesterday last class continuation. So up to what have we done last class? Block storage. Up to block storage. Okay, so let me share the screen. So in our last class, we have seen about index compression. Okay, index compression. So here in index compression, once again, let me just go through. We are going to compress the size of the dictionary so that we can achieve having an efficient IR system. Okay, so two types of compression was there, lossless compression and lossy compression. And we have also seen calculating the vocabulary size using Hicks law, and also we have seen distribution of the terms using Gibbs law. Calculations has been done, finding the probability, and dictionary compression was our last class. In our last class, we have seen about dictionary compression. So in dictionary compression, what we have done was we normally compress the size of the dictionary using fixed width entries. Okay, so we store the dictionary having a fixed width entry. So using fixed width entry, we have certain disadvantages. Some of the disadvantages are we simply fix the length of the array as fixed. So normally the size of the string for an English character for an English word is about 8 characters. The average length is about 8 characters, which means we require in an average of 8 bytes. But here what we have done was we have stored 20 bytes for a um, particular term. So sometimes, one second. So sometimes, what is the disadvantage? Here, the average length is about 8 characters, but we have put the size as fixed, about 20 bytes. So remaining 12 bytes are already wasted. Okay, so we have wasted the number of bytes here because you can see here the term Zulu, it has only 4 bytes, but since it is a fixed byte storage, 20 bytes is already occupied. So 4 bytes is stored in 20 bytes, 16 bytes are wasted like this. Here we have only 6 characters, that means 6 bytes, and we have fixed storage as 20 bytes. So 20 minus 6, 14 bytes is wasted. So like this, on an average, we have wasted about how many bytes? We have wasted about 12 bytes for every term in the dictionary. So in order to uh, avoid this, to overcome the problem, we have started a technique, new compression technique, which is dictionary compression as a string. Dictionary compression as a string. So, and one more disadvantage for fixed width entry is here sometimes when we have terms, the length is more than 20 characters. If we have terms which is more than 20 characters, in that case, we cannot store that particular term. because we have fixed with entry which is 20 bytes only. Hydrochlorofluorocarbons uses more than 20 bytes. This cannot be stored in the memory. So this is also one of the disadvantages we have in dictionary compression using fixed with entry. But in dictionary compression as a string, we have done in a different way, slightly different from the fixed with entry. Here, what we have done is we have put the dictionary as a string. So, as a long string, we consider the dictionary as a long string and we put some pointers at the beginning of the terms. Suppose here SYSTILE. So it's a style. Here we have put one pointer. So this indicates it starts a term, new term. For one more pointer is here, the second pointer. It points at S. This means it starts the new term from this S. So the style is diegetic. Like this, we have certain 3, 4, 5 terms here. Okay. So for this also we have seen that for document frequency, it is 4 bytes. For posting pointer, it is another 4 bytes, and for term pointer. So here, for every term, we have used a pointer. So for term pointer, 3 bytes. And we also have seen the calculation how many bytes or how many storage does it require. So for this one, 4 bytes for term frequency, 4 bytes for frequency, 4 bytes for pointer, and 8 bytes if we consider on an average for term in string, and 3 bytes per pointer into string. So how this 3 byte comes? This calculation has been shown here for your understanding purpose, and we follow the calculation here. So this 4 lakhs is nothing but from this Reader's dictionary we have taken the number of terms as a reference number. So using this number from Reader's number of terms, so we have 4 lakh terms and 4 pointer, 4 bytes for frequency, 4 bytes for pointer, 3 bytes for your term pointer, and 8 bytes for average length of the term in the dictionary. So we have got 7.6 MB. But for dictionary as a compression, dictionary as fixed with entry, we have got 11.2 MB. So the size has been reduced from 11.2 MB to 7.6 MB. So we have reduced about 3 MB something, 3 point MB something. Okay. So this shows that the compression technique dictionary as a string is better than dictionary compression using fixed with entry. But again, we also have another compression technique known as block storage. So in block storage, here also almost similar with the dictionary as a string, but we apply the concept of block sort based storage concept here in dictionary compression. How? Here we have compressed the dictionary by grouping the terms in the string into blocks of equal size. Blocks of size k, just like what we have done in block sort based storage, block sort based indexing. So taking the concept of block sort based indexing, in block storage we have blocks of size k, and also we have term pointer only for the first term of each block. We have the term pointer only for the first term of each block. In dictionary as a string, for every terms we have the term pointer, but in block storage we have the the term pointer only for the first term of each block. If we have 5 blocks, then there will be 5 pointers only. So in a block, it may contain 4 or 5 terms accordingly, since block of size k. So number of terms may be 5, it may contain 5, it may contain 4. So in this particular example, the block size, we have 4 terms per block. We have 4 terms per block. So each block will have one term pointer only. That means at the beginning of the term, the first term alone, we will be having the pointer. Instead of having every single pointer for every terms, we have only put for a block only one pointer pointing to the first term of each block. Now, here the condition is we are putting the length of the term before here. The pointer will be pointing to the length of the term. Suppose systile has 7 characters, so 7 will be putting in front of the term. So like that, for every term, we are putting the term length in front of it. So for this, we need extra storage. How? Let us see here. This has been done already. Just I'm giving you brief revision for this block storage. Okay. So you can see here, since we have 4 blocks, 4 pointers will be there, and for the remaining 3 pointers, we will be saving 3 bytes, 3 bytes, 3 bytes each. Because for term pointer, it is 3 bytes. So term pointer, since we have 4 blocks, only for first block is being used, being given the this one for 7 only. We have put the pointer, so term pointer 3 will be utilized. The actual term pointer will be 4 into 3, 12 bytes should be utilized, but since we use term pointer only for the first term, only 3 bytes will be utilized. So 9 bytes will be saved. Now you can see here systile one term, syzygetic one term. It has 9 characters, so we are putting the term length here 9. Syzygial 8 characters, so 8 bytes. We are putting the term length 8 in front of it. And for 6 syzygy, also it has 6 characters, so we are putting 6 here. So this is one block. Up to this 4 terms, it is one block. And another block starts from gibelliite, something, gibelliite. So it starts from this, another 4 terms, it will have another block. So for this first block, we have one term pointer here. One term pointer. This is the first term of the block. So we are putting the term pointer here. That means 3 bytes will be utilized. Okay. So and for this, since we don't use the 3 term pointers for this remaining 3 terms, so 3 bytes for 3 terms, 3 into 3, 9 bytes has been saved. Okay. Now for term length, 7, 9, 8, 6, we are putting the term length, right? For this, we another need 4 bytes. So total 9 bytes has been saved and 4 bytes has been again used for term length. So 9 minus 4, 5 bytes. So we can save only 5 bytes. So now next one, the calculation has been done here. So this is what just now I have said. Initially, if every term has been assigned a term pointer, it will be 12 bytes for term pointers. Okay, but now since only one term pointer has been utilized out of 4 term pointers in a block, we have saved 9 bytes. So explanation here. Okay. So let us do the calculation, space requirements. So space requirements, since only 1 byte One term pointer has been utilized out of four, and five pointers has been saved. So after calculating the storage requirement, it reduces to 7.1 MB. Initially it was 7.6 for dictionary as a string, but now block storage it is 7.1 MB. Okay, now you see here. So by increasing the block size k, we get better compression. Okay, so you can see here by increasing the block size k, we can get better compression. So again, however, there is a trade-off between compression and the speed of term lookup. So let us see an example to understand about the storage, block storage. So we have search for the uncompressed dictionary A. The figure A shows the uncompressed dictionary searching and dictionary compressed by blocking with k equal to 4. By blocking with k equal to 4. So here, since it is uncompressed, you can start searching from job to then to box to add, then to X like this. So normal searching without any compression technique. Okay. But here in B, we have block size of 4. Block size k equal to 4. So we have 4 terms in the first block and we have another 4 terms in the second block. 8 boxed, then X. So this is one block and job, ox, pit, win. This is another block. So we have size k equal to 4, which means term equal to 4. 4 terms each. So we have 2 blocks here. Now, since we separate the uh, dictionary into 2 blocks, we can easily perform the search operation. So you can see here in the example, searching the uncompressed dictionary takes on average of 0, 1, 2, 3, 2, 1, 2 divided by 8, which is 1.6 steps. How? So here, that means from here 1, from job another 1, 2, from job 1, 2, 3, like this. So this is the starting point. We are going to search from here to then if we want to search one step. From job if we want to search 2 steps. From job if we want to search at another 3 steps. And from job you want to search X another 2 steps like this. So if we calculate all the steps on an average, so since it is of 8 terms, 1, 2, 3, 4, 5, 6, 7, 8 terms, on an average we need about 1.6 steps. So finding 2 terms, you can see here, for example, finding 2 terms, add and box takes 3 and 2 steps respectively. So this is what I have explained here. If you want to find add and box, if you want to find add and box, so from here you have to search 1, 2 steps, and for add 1, 2, 3 steps. So 2 and 3 steps. That is what it is said here. For finding the 2 terms at and box, it takes 3 and 2 steps respectively. For add, it takes 3 steps. For box, it takes 2 steps. Now, with blocks of size k equal to 4, we need 0 plus 1 plus 2 plus 3 plus 4 divided by 8, which is 2 steps on average. That is 25% more. So for example, if you want to search from here, you can search directly like this. You don't need to go back. Here, suppose if you want to search X, you have to search like this. So here, directly you don't need to go back. You have to go like this. In this first block, you can search blockwise. You can search for this block, for this block. So explanation we will do once again for calculation. So for finding, then takes one binary search step. For finding, then. For finding, then it takes one binary search. That means 1, 2. Oh, sorry. From this is one box, this is one box. 1, 2. So it takes two steps. Now, here by increasing k, we get the size of the compressed dictionary close to the minimum. Close to the minimum of, this is 4 lakh terms, 4 bytes for frequency, and this is for another term pointer and average length, and this is for your this block. So for term lookup becomes slow for large value of k, but when you increase the size, it has both advantage and disadvantage. We are talking about size k increasing, right? So when you increase the size, it will take longer lookup time, okay, but your size will be reduced. That is what it is said here. For increasing k value, we can get a reduced size minimum storage capacity, whereas the term lookup will have longer time because it will be slow for large value of k. So here the advantages for block storage is we can have lesser size, lesser storage in the memory, whereas the term lookup will be more, it will take more time, so it will be slow. So once again, we will see the example. We will extend from here. Where is it? Here. Okay. So block storage, what we have done was block storage, right? So block storage, I have explained we can say 5 bytes, and if we say 5 bytes, the size is reduced to 7.1 MB. But now there is another point in block storage. Okay, there is another point. What is the point here? When we increase the size of the k, when we increase the size of the k, we can have better compression. That means our memory can be, the size can be reduced than before, but the speed for searching may be slow. The speed for searching the particular term may be slow. So let us see how. We have two examples here, A and B. First, A is the uncompressed dictionary without applying any compression technique here. So for particular searching a particular term, we need to search from this one. So since from this is the starting point, we can search from here. If we want to search box, then the same line we have to go 1, 2. Again, if you want to search at, we have to go from again this line 1, 2, 3, like this. And like this, it can go, the already path is there, you can check, you can go to any path. If you want to search win, like this. Okay. But in dictionary compression, by the method of blocking, we can divide the particular dictionary into blocks of size k. and two blocks of size k. Here we consider k equal to 4. We consider k equal to 4. So we have a block here, 8, box, then X. And we have another block here, job, ox, feet, win. So you can either search blockwise. If I give you then, if you want to find then, you don't need to search from job because it is one block. It is one block. So you can search here directly. So it takes only one binary step. One binary step means it takes only two steps. So like this per block wise, so we reduce searching from job. And now here the calculation comes. So on an average, this 1, 2, 3, 2, 1, 2, and 2. This is nothing but see from job. If you want to search, this is one step. From box to job, two steps. From box to add, three steps. From box to X, two steps. Like this. From job to pit, one step. So two steps like this. So this is what it is written here. And if we want to find the average for searching the uncompressed dictionary, it may take about 1.6 steps. Okay, steps. This is not the size. This is not the size. This is number of steps. So time, the speed of searching. So speed of searching is less in uncompressed dictionary because when you increase k size, the term lookup, that means when you search a term, it may take longer time. But your size of the dictionary will be reduced more than the previous technique. So here with block size k equal to 4, it takes on an average of 2 steps. Whereas for an uncompressed dictionary, it takes on an average of 1.6 steps. So this is also same like how we have done here. 1, 2, 3. If you start from job, 1, 2, 3, 4. If you start from job to search win, 1, 2, 3, and 1, 2 like this. Okay. So on an average, just you remember here the concept of block storage when you increase size k. The size of the k, the concept here is nothing but it's very simple. The dictionary compression, the size may reduce more. Okay, the memory for space requirements may reduce more when you increase the size of the k. But the speed for searching the term may take longer time. The speed for searching the term may take longer time, whereas the space requirement may be reduced more. Okay. So here it takes about 6.8 MB space requirements using block storage when we increase the size of the K. Now front coding. Front coding, it is like another type of compression technique. Here sorted words commonly have long common prefix. So store differences only. We are going to store the differences only. Let us see so that we can understand it. One block in blocked compression when size k equal to 4. So we have 8 terms here. We have 4 terms here. K equal to 4 means number of terms. So we have k equal to 4. We have 4 words. What are the words? Automata, automate, automatic, and automation. Automata, automate, automatic, and automation. Similarly, with block storage, we have written the term length in front of the term. So, AUTOMATA, 8 characters. So, 8 bytes we have written down here. Automate, AUTOMATE, another 8 characters. So, this has been written here. So, similarly, for automatic, the term length is 9. For automation, the term length is 10. So, it is written down here. So this will be compressed with front coding. Front coding. We will apply some coding method here in uh, this block. So you can see here automate. We are going to write E. Automate. We are going to write E. So you can see here a sequence of terms with identical prefix. Identical prefix is encoded by marking the end of the prefix with star, asterisk. Okay, so those identical uh, prefix will be encoded by marking the end of the prefix with asterisk and replacing it with diamond symbol. Okay, in subsequent terms, replacing it with diamond symbol in subsequent terms. As before, the first byte of each entry encodes the number of characters. So that means first byte is nothing but this first byte is 8. 8 encodes the term length. Term length. So this is has been explained already. Now you see here A is encoded as 1. So A is encoded as 1. E is encoded as 2 and IT. So automata O AUTOMA. So next word here is A. So A is here we have encoded. A is encoded. Now you see here E. AUTOMAT. So up to automate is equal. Right. Up to automate is same for all the 4 terms. You can see here AUTOMAT. 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 So all the 4 terms has equal strings up to automat. AUTOMAT. So after that we have what? See here we have A. We have E here. We have A in the first uh, term, E in the second term. In the third term, IC. In the fourth term, ION. So that has been added at the end of it. Okay, instead of writing all the 4 terms here, we have just written by encoding it. So A is encoded. And for the second one, E is encoded. And for the next one, IC is encoded. And for the final one, ION is encoded. Okay. So this is what we have done in front coding. So this will reduce the size of the memory. Space requirements will be reduced because instead of writing the full length automata, automate, automatic, automation, so we have checked the spelling here up to automate MAT is equal for all the 4 terms, right? O A O T A U T O M A T A U T O M A T. Here also AUTOMAT, automate. It is equal for all the four terms. We have just taken it as a common word automate here, and the remaining word A is not written, so A is encoded here. So we put what? For identical terms with identical prefix. So automate is the prefix. Automate is equal for all the terms. So we have written automate here. And the remaining word automata A is missing, right? So this A will be added by marking the end of the prefix with star. So star at the end of the prefix, we have put a star here, right? At the end of the prefix, we have put a star and replacing it with diamond symbol in subsequent terms. And for subsequent terms, it will be replacing by diamond symbol. And here the term length is written in the first byte of its entry. This indicates the term length. So you can easily understand by seeing the example here. Up to automate is the same identical prefix, and for the first one A is missing. Now A is 1 because length of the A we have added here 1. And for, where is it? Next one is E is missing. E is added here. Next one IC is missing. IC is added here. Next one ION is missing. ION is added here. So we put some numbering here, right? 1, 2, 3. So this will add as extra length to the and another 1, 2, 4, 5, 6, 7. So we will see the calculation. Front called calculation. Okay, calculation we will see in the other slide. This is directly they have shown the reduced one, 5.9 MB. 5.9 MB. 6.8 was for block storage with increasing K size, and with front coding it has been reduced to 5.9. So calculation we will see in the next slide. Here they have shown only the reduced size. Why? Because blocking plus front coding. Here front coding. So we put some coding here. We put some coding here instead of writing the same word automate. Automate is similar in automata. Automate again automatic automation. So the identical prefix here is automat, AUTOMAT. So AUTOMAT is same for all the four terms. So we have taken this as common, and the remaining words, the missing words, we have encoded at the end using some coding, using some coding. Okay, so that is what we have done here. A which was missing in automata, we have put here. E which was missing in automate, we have put here. Then IC which was missing in automatic, we have put here. And ION which was missing in automation, we have put here. So after calculation, we got 5.9 MB. The size has been reduced to 5.9 MB. Okay, we will see the calculation. Calculation is not in this slide. So calculation we will do tomorrow. The same thing, only the how it's been being calculated here. It will be for term. This one, no, for lakh terms will be there, and here we won't be putting the term pointers. Term pointers won't be there, but your this term length pointer, term length for bytes will be there, because for term length, what is, where is it? Term length we use four pointers, right? In block storage we use four pointers, right? For term length, here. So for frequency 4 bytes, for term pointer 4 bytes, then for posting list 4 bytes, and 8 bytes on an average for term and string, and 3 bytes for term pointer. So these 3 bytes will be reduced in your this one front coding, because we are not going to use the term pointer. We will be using the posting list pointer, which is 4 bytes for frequency. We will be using 4 bytes, and 8 bytes for an average. This will be using, and this one be using. So the size will be, where is it? 5.9 MB approximately. So space requirements is reduced. So fixed width, the space requirement is 11.2. Dictionary as a string, the space requirement is 7.6. And block storage, when k equal to 4, the size is, space requirement is 7.1. And blocking plus front coding, again this will reduce more. It is 5.9 MB. Okay, so next one. The next one, it's time already. We will see this next topic in our next class. We'll take the roll call now. Just give me 1 second. I think I have sent study material for this in your Google Classroom group already. You can refer that. There also the calculations will be there. Okay. Next class also we will see about this once again, because this might be a little confusing, all the compression techniques. But you just need to understand the concept. In dictionary compression, using fixed length, what is the method? And in dictionary compression as a string, what is the method? Block storage, what is the method? And block storage plus front coding, what is the method? That has to be understood properly. Once you understand the concept, then easily you can know the calculations and all. Okay, but anyway, we will see all those calculations once again tomorrow. How the sizes are reduced according to the different compression techniques being used. So we will see that tomorrow. For today, uh, we don't have much time left, so I'll take a roll call. You answer to your roll call. Roll number one,
Present, ma'am.
roll number two,
Present, ma'am.
roll number three,
Present, ma'am.
roll number four,